There's something strange showing up in almost every single picture we take of the early universe. Tiny red dots. They are scattered across the oldest and most distant regions we have ever managed to photograph, and no matter where we point our telescope, they keep appearing again and again. And yet, even after years of study, nobody can say for certain what these things actually are. The more scientists learn about them, the stranger they seem to get. These little red dots do not match anything we already know about how stars, galaxies, or black holes are supposed to form. Objects, this ancient, are supposed to be small, messy, and still slowly gathering mass. Instead, these dots are unbelievably dense, shockingly bright, and carrying far more mass than anything that old should have. So what exactly are we looking at? Some scientists now believe these little red dots might be something the universe has never shown us before, a strange hybrid object that behaves like both a star and a black hole at the same time. Is that even something nature can produce? And if it is real, what does that mean for everything we thought we understood about how the early universe came together? Today, we are going to break down why these little red dots have confused astronomers for years, walk through the competing explanations scientists have proposed, and look at the newest evidence that might finally be settling this mystery. Because it could be the missing clue behind one of the biggest unanswered questions in space science, how the very first giant black holes were born. This is not a small, niche question either. The origin of supermassive black holes sits right at the center of how we think galaxies, including our own, came to exist in the first place. Almost every large galaxy we know of has one of these giants sitting quietly at its core, and yet nobody has ever directly watched one form from scratch. If little red dots really do turn out to be an early, transitional phase in a black hole's life, we may be looking at the closest thing to a birth certificate for these objects that astronomy has ever managed to capture. These strange points of light were first noticed in surveys designed to search for the earliest galaxies in existence. Observational programs built to peer back to a time between roughly 500 million and 1 billion years after the Big Bang. Astronomers were not specifically looking for little red dots. They just kept appearing, uninvited, in image after image. As James Webb kept scanning deeper into the sky, nearly every picture it returned from this ancient era contained the same strange glowing point. By around 600 million years after the Big Bang, the early universe appears to have been absolutely packed with them. Then, roughly 1 billion years later, they vanish almost entirely from the record. That disappearing act alone was enough to turn them into one of the strangest puzzles in modern astronomy. But what do we actually know about these objects so far? To begin with, they are remarkably small, usually no more than a few hundred light years across, which is roughly 200 times smaller than our own galaxy. Despite their tiny size, they burn unusually bright, and they glow with a strong reddish color, which is exactly why nobody had spotted them before. Earlier telescopes simply were not built to see them. Hubble was tuned to detect shorter wavelengths of light than the ones coming from these mysterious dots, and no earlier telescope had the raw power needed to look this far back across cosmic history. James Webb is essentially the first instrument ever built with the specific sensitivity needed to pick up the infrared wavelengths these ancient objects give off. By combining two of its instruments, one built for near-infrared imaging and another tuned for the mid-infrared range, astronomers finally caught a proper look at these ancient objects. Even so, it took until a landmark paper published in March 2024 for their basic properties to be formally documented and given a name. Since that first formal description, the catalog of confirmed little red dots has grown steadily larger. By 2025, researchers had already identified and logged several hundred of them scattered across different deep field surveys, and that number keeps climbing every time a new observing campaign wraps up. What makes this especially strange is the sheer consistency of the pattern. These are not a handful of unusual one-off objects that showed up by chance in a single image. They are a genuine population, spread across completely different regions of the sky, all sharing the same bizarre set of properties, and all clustered within the exact same narrow window of cosmic history. Now, most people already know that older objects in space tend to look redder to us, thanks to an effect called redshift. Because the universe is constantly expanding, the space itself, along with the light traveling through it, gets stretched out. The longer that light has been traveling, the more its wavelength gets pulled and lengthened, and the redder it appears by the time it reaches our telescopes. But when astronomers actually broke apart the light from these little red dots into its individual wavelengths, they discovered that redshift alone could not explain how red they really looked. Something extra was going on. The first guess was dust. Tiny dust particles are much better at scattering short, blue wavelengths of light than longer, red ones, which is the exact same reason our own sunset looks red as sunlight passes through more of Earth's atmosphere near the horizon. If a thick cloud of dust surrounded these objects, that alone might explain the excess redness. It is worth pointing out just how reasonable the dust explanation seemed at the time. Dust is an incredibly common ingredient inside galaxies, and reddening caused by dust is one of the most well understood effects in all of observational astronomy. If you had shown early results on these little red dots to almost any astronomer a decade ago, dust would have been the first and most obvious guess, and for good reason. It is exactly the kind of simple, well-tested explanation that usually turns out to be correct. This time, though, the data had other plans. To test that idea, researchers turned to a specialized instrument built to split incoming light apart into a detailed spectrum. What they found only deepened the confusion. The spectrograph takes light from a distant object and separates it into its individual component wavelengths. Different chemical elements absorb light at very specific wavelengths, leaving behind gaps in the spectrum almost like a fingerprint. So if something, like a cloud of dust or gas, sits between the telescope and the source of light, some wavelengths simply will not make it through. By studying exactly which wavelengths go missing, scientists can work out what that intervening material is actually made of. What they noticed was that these little red dots gave off plenty of blue and ultraviolet light, plenty of red and infrared light, but comparatively little in between. That produced an unusual, sharply angled shape in their spectrum, almost like a V. Nothing previously known from the distant universe matched a spectral fingerprint quite like it. There was, however, one useful clue buried in the data. At a very specific wavelength, close to 365 nanometers, the spectrum suddenly jumps upward. Light with a wavelength shorter than this point kept getting absorbed, while anything with a longer wavelength passed through largely undisturbed. This particular pattern already has a name in astronomy, a Balmer break. And whenever scientists see this signature in a galaxy, there is usually one very reliable explanation behind it, a large population of young, extremely hot stars. To understand why, it helps to picture the electrons inside a hydrogen atom sitting on fixed rungs of a ladder, each rung representing a specific allowed energy level. A photon can only be absorbed by an electron if it carries exactly the right amount of energy to knock that electron up to a higher rung. Because hydrogen atoms have a very particular internal structure, there is one especially important wavelength where this effect becomes dramatic, roughly 365 nanometers, which corresponds to the exact energy needed to strip an electron away from a certain energy level entirely. Any photon with a shorter wavelength than that carries enough energy to be absorbed this way, while anything with a longer wavelength simply passes straight through undisturbed. That sharp cutoff is what creates the break scientists were seeing, and its presence is essentially a signature, confirming that a large amount of relatively pure hydrogen gas sits somewhere between the light source and our telescope. For a while, it looked like the mystery might be solved. Perhaps these little red dots were simply very early, compact galaxies bursting with new star formation. It would have been an elegant, tidy explanation. Unfortunately, elegant explanations rarely survive contact with more data. So the first serious theory on the table was that these objects were starburst galaxies, meaning galaxies undergoing an intense, rapid wave of star formation. This idea had a lot going for it at first. Hot, young stars are rich in hydrogen, which could plausibly explain the strong Balmer break in the spectrum. A tightly packed population of stars could also explain the brightness. And if these young galaxies were full of dust, as starburst galaxies typically are, that could account for the reddish color too. It seemed almost like a perfect fit, except for one stubborn detail. The numbers simply refused to add up. Researchers quickly ran into two serious obstacles. The first was the sheer amount of dust required. Dust inside galaxies mostly comes from one source, stars themselves. And there is a well-established relationship between how many stars a galaxy contains and how much dust that population is expected to produce. When scientists calculated the expected stellar population of these little red dots based on their observed light, and then applied the standard star-to-dust ratio, the results were alarming. Their calculations only produced about 1% of the dust needed to actually explain the redness being observed. A shortfall that large, roughly 100 times too little, could only mean one of two things. Either our long-standing models of dust formation were fundamentally wrong, or the primary light source inside these little red dots was not ordinary starlight at all. The second problem involved brightness. To explain how bright these objects appeared using nothing but stars, you would need an almost impossibly dense concentration of stars crammed into an extremely small volume of space. Stars would need to be packed just a few astronomical units apart from each other. At that kind of density, stars would constantly be colliding and merging, and the whole system would be gravitationally unstable almost immediately. On top of that, these little red dots simply do not look like typical galaxies. Normally, even distant galaxies show some visible internal structure once you study them closely enough. But despite James Webb having the sharpest resolution of any telescope ever built, these little red dots still appear as nothing more than single points of light, much like ordinary stars look to the naked eye. So either these objects really were impossibly compact, or their light was so overwhelmingly dominated by one central source that it was simply drowning out any surrounding structure that might otherwise be visible. Which brings us to the second major theory that scientists began seriously considering. What if these little red dots were not young, star-packed galaxies at all? What if something else entirely was producing that light? At the heart of nearly every large galaxy sits a supermassive black hole, usually surrounded by a swirling disk of infalling gas and dust known as an accretion disk. As material spirals inward toward the black hole, it becomes compressed and superheated to temperatures well above 10 million degrees, releasing an intense glow in the process. Actively feeding black holes are consistently among the brightest single objects in the entire universe. Could that be what was hiding behind these little red dots? Surrounding the accretion disk of an active black hole is often a thick, donut-shaped ring of gas and dust called a torus. If you happen to be viewing that torus edge on, the surrounding material sits directly between the observer and the glowing black hole underneath, absorbing the shorter wavelengths of light while letting the longer red and infrared wavelengths pass through relatively freely. That should sound familiar, because it lines up almost perfectly with what scientists were already seeing. Treating little red dots as hidden black holes made a lot of sense at first. It would explain the extreme brightness, the point-like appearance, and the strong reddish color all at once. As an added piece of supporting evidence, the emission lines in their spectra were unusually broad, which typically indicates large amounts of gas orbiting something at extremely high speeds. Gas moving toward the observer gets slightly blue shifted, while gas moving away gets slightly red shifted. And when you combine both effects together across an entire spinning disk, the resulting spectral lines get stretched wider than usual. The faster that orbiting material moves, the broader those lines become. Exactly the pattern you would expect from a massive black hole actively pulling in large amounts of surrounding gas. For a while, the black hole explanation looked extremely promising. That optimism did not last long, because researchers soon noticed something important was conspicuously absent. As far as astronomers understand it, actively feeding black holes should almost always give off strong X-ray emission from their superheated accretion disks. But when scientists carefully measured these little red dots, they found essentially no X-ray signal at all. That was a serious blow to the black hole explanation. And there was a second problem waiting right behind the first one. The apparent black holes seemed dramatically oversized compared to the tiny galaxies they were supposedly sitting inside. In the nearby present-day universe, a typical supermassive black hole makes up only around 0.1% of the total mass of its host galaxy. This relationship shows up so consistently across countless galaxies that astronomers believe black holes and their host galaxies must grow together in some kind of coordinated feedback loop, keeping their relative sizes locked in step with one another over time. But when researchers measured the apparent black holes powering these little red dots, the ratios were wildly different, sometimes closer to 10% of the total galaxy mass instead of 0.1%. It looked almost as though these black holes had somehow ballooned to enormous size before their surrounding galaxies had even had the chance to properly form around them. One astrophysicist working closely with this data summed up the dilemma neatly at the time, pointing out that if these objects really did contain black holes, those black holes were simply too large for such tiny galaxies to host. But if the light was coming purely from stars instead, the galaxies would need to be packed at densities that seemed almost physically unthinkable. Either explanation, taken on its own, kept running into a wall. Both leading theories, the starburst galaxy idea and the hidden black hole idea, had real strengths, and yet neither one could fully explain everything scientists were observing in these little red dots. It genuinely seemed like these objects were sitting somewhere in between two categories that were never supposed to overlap. So if little red dots were not simply young galaxies bursting with stars, and they were not ordinary feeding black holes either, what were they? Was it possible astronomers had accidentally discovered an entirely new type of object, something the universe had never revealed to us before? That was exactly the question a growing number of research teams set out to answer through the mid-2020s, launching dedicated surveys aimed at collecting the deepest, most detailed spectra ever obtained from these mysterious objects. Rather than relying on shallow snapshots, these programs poured dozens of hours of valuable telescope time into individual targets, hoping to finally capture enough detail to settle the debate once and for all. One especially important breakthrough came together in June of 2026, when a research team led by an astronomer at the University of Texas at Austin published the single most detailed spectrum ever taken of a little red dot. Rather than observing an isolated target directly, the team took advantage of a natural cosmic magnifying glass. They aimed James Webb at a massive galaxy cluster known to bend and focus the light of much more distant background objects through gravitational lensing, an effect first predicted by Einstein's theory of general relativity and confirmed by observation decades ago. Sitting behind that cluster, at a distance corresponding to roughly 1.8 billion years after the Big Bang, was a little red dot whose light happened to pass directly through the cluster's gravitational field on its way to us. The cluster's enormous mass warped that light, stretching and magnifying it dramatically. In practical terms, 30 hours of actual telescope time produced a signal roughly as strong as what would normally require around 80 hours of direct observation. No little red dot had ever been studied with this level of detail before. The resulting spectrum contained more than 40 distinct spectral lines, by far the richest set of clues ever extracted from a single one of these objects. And when researchers examined all 40 of those lines together, nearly every single one of them pointed toward the same underlying explanation. To appreciate why this particular observation mattered so much, it helps to understand just how faint these objects usually are. A typical little red dot sitting at these extreme distances is so dim that even with James Webb's incredible sensitivity, a standard spectrum only reveals a handful of the very brightest features, just enough to hint at a possible explanation, but nowhere near enough to rule out the alternatives with confidence. Every competing theory could point to some of those features and claim a partial match. What was missing was a single object bright enough, or magnified enough, to reveal dozens of fainter diagnostic details all at once, each one independently constraining the density, temperature, and structure of the gas involved. Gravitational lensing was what finally made that possible, turning an otherwise unremarkable distant object into the best-studied little red dot in existence almost overnight. Among the specific features found in that spectrum was something researchers call an iron forest, a dense cluster of overlapping emission lines produced by ionized iron, a signature already well known from actively feeding black holes closer to home. Alongside it were absorption features from helium, indicating a highly ionized gas environment, and a handful of fluorescent signatures that only appear when gas is bathed in an extremely intense field of ultraviolet radiation. Exactly the kind of environment you would expect surrounding an actively accreting black hole rather than a simple population of forming stars. Taken individually, each of these clues might be explained away. Taken together, in a single object, they formed a remarkably consistent picture. That explanation is often described as a black hole wrapped inside a star-like disguise. At the very center sits a genuine, rapidly feeding, supermassive black hole, likely consuming gas faster than the theoretical limit normally allowed for black holes of its size. That inner accretion disk still produces intense, high-energy radiation, including plenty of ultraviolet light and X-rays. This single model elegantly explains three of the most puzzling features scientists had been struggling with all along: the strong red color, the almost total absence of X-rays, and the unusually broad emission lines. The redness comes from the gas cocoon filtering out shorter wavelengths. The missing X-rays are not actually missing at all. They are simply trapped, absorbed by the surrounding gas before they can reach our telescopes. And the broad emission lines turn out to come from photons repeatedly bouncing and scattering off electrons inside that dense cocoon, rather than purely from gas orbiting at extreme velocity, the way scientists originally assumed. That distinction turns out to matter enormously, because it also solves the earlier puzzle of oversized black holes. When photons scatter repeatedly through a thick gas envelope before finally escaping, each bounce slightly shifts their wavelength, and the cumulative effect makes emission lines appear far broader than they really should be. Scientists studying these systems in detail found that once you properly account for this scattering effect, the estimated mass of the central black hole drops dramatically, often by roughly a factor of 100 compared to earlier calculations. Suddenly, these black holes were no longer wildly oversized for their host galaxies. Instead, their masses fell much closer to the familiar ratio we already see in galaxies much closer to home. In other words, the universe was never actually broken. Astronomers had simply been measuring these objects through a thick fog they did not yet know was there. This particular breakthrough did not appear out of nowhere. It built directly on an earlier study published at the start of 2026, which analyzed a dozen separate little red dots and reached a similar conclusion: that the black holes inside these objects were likely around 100 times less massive than initial estimates had suggested, bringing their numbers back into line with what standard models of black hole growth would actually predict for the early universe. Even with this growing convergence of evidence, the story is far from fully settled. A separate group of researchers proposed a genuinely different explanation around the same time, suggesting that at least some little red dots might not be black holes wrapped in gas at all, but rather an entirely different kind of exotic object. Enormous, short-lived stars, potentially reaching masses close to 1,000,000 times that of our Sun, caught in the final dramatic moments before collapsing directly into a black hole. Under this idea, these giant primordial stars would still be powered mostly by nuclear fusion in their extended, puffed-up outer layers, rather than by an active accretion disk, yet they could still produce a similar reddish glow due to their unusually large, diffuse structure lowering their surface temperature. This competing idea has not been ruled out, and it may turn out that little red dots are not one single uniform category of object at all, but a mix of several different exotic phenomena, that all happen to look remarkably similar from a distance, at least until you gather enough spectral detail to tell them apart. Adding even more texture to the picture, a separate research effort published in early 2026 studied a large sample of little red dots and discovered something unexpected sitting right next to many of them. Close to half of the little red dots examined had a small companion object nearby, an ultraviolet bright source situated a short cosmic distance away, sometimes just a few thousand light years off. Researchers are still working out whether these faint companions formed first and somehow helped trigger the growth of the central black hole star sitting beside them, or whether the relationship works the other way around. Either way, it suggests these strange objects may not exist in total isolation, but might instead be tangled up with the very earliest stages of galaxy assembly happening around them. There's also the deeper question nobody has fully answered yet. Where did the seeds of these black holes even come from in the first place? According to newer theoretical work published in the middle of 2026, the earliest black hole seeds may have started forming shockingly early, less than 200 million years after the Big Bang, inside small pockets of dark matter left behind by the very first generation of stars ever to exist. These initial seeds would already sit somewhere in what astronomers call the intermediate mass range, but nowhere close to large enough to power a fully formed little red dot on their own. The proposed solution is a process involving short, violent bursts of extremely rapid feeding, sometimes referred to as nuclear bursts, during which a black hole gulps down surrounding gas at roughly 10 times its theoretical maximum feeding rate for brief periods. According to this model, it is this repeated cycle of explosive overfeeding, rather than slow, steady growth, that eventually pushes these early black hole seeds all the way up into the 100,000 to 1 million solar mass range, by the time we observe them glowing as little red dots around 1 billion years after the Big Bang. If that picture holds up, it would offer a genuinely satisfying answer to one of the biggest outstanding puzzles in astrophysics. How do supermassive black holes manage to grow so enormous so early in cosmic history, when the conventional slow and steady growth process should take many billions of years longer than the universe had actually been around at that point? It is worth remembering that all of this research is still moving extremely fast. New papers on little red dots are being published at a pace that is difficult for even dedicated researchers to keep up with. And the field has shifted multiple times over just the past 2 years as better data has continued to arrive. The black hole star explanation currently has the strongest and most complete body of evidence behind it. But competing ideas, including the giant primordial star hypothesis, have not been fully ruled out, and there are still plenty of open questions left to answer. How common is this violent feeding phase in a black hole's early life? How long does it typically last before the surrounding gas cocoon disperses or gets blown away entirely? And why do these objects vanish so abruptly from our surveys, roughly 1 billion years after the Big Bang, never to be seen again in quite the same form? Whatever the final answer turns out to be, one thing is already clear. These little red dots are not just a curious footnote in James Webb's growing catalog of discoveries. They may be showing us, in real time, the missing early chapter of how the universe's first giant black holes came into existence, a chapter that, until very recently, we did not even know we were missing. And with more deeply lensed targets already being lined up for future observation, it looks like we're only just beginning to read it properly. There is also something worth reflecting on beyond the pure science here. For years, this population of objects was labeled as a threat to standard cosmology itself, with some scientists openly worrying that our basic understanding of how the early universe assembled might be fundamentally wrong. That kind of headline tends to spread fast because it suggests something dramatic and unsettling, that the rulebook governing the cosmos might need to be thrown out entirely. What the newest, deepest observations are now suggesting is a little less dramatic, but arguably even more interesting. The universe was not broken after all. Our instruments simply were not yet sensitive enough to see through the disguise these objects were wearing. Once astronomers gathered enough light to look past that gas cocoon, the numbers lined up far more comfortably with existing theory than anyone expected just a couple of years ago. That is often how the biggest mysteries in astronomy tend to resolve themselves, not with a single dramatic announcement, but with a slow accumulation of better data, sharper instruments, and more careful analysis, gradually turning something that once looked impossible into something that finally makes sense. Little red dots may end up being remembered less as a crisis for cosmology, and more as a lesson in patience. A reminder that when the universe hands us something we cannot explain, the right response is not to panic, but to keep looking more closely until the picture comes into focus. It is a genuinely rare thing to watch a scientific mystery unfold this openly, with new papers, new observations, and new competing ideas arriving almost every few months. Most of the time, by the point a discovery reaches the public, the debate behind it has already quieted down. With little red dots, we are getting to watch the argument happen in near real time. models rising and falling as fresh data comes in, and that makes this one of the more exciting stories in astronomy to follow right now. If you found this breakdown interesting, make sure to subscribe so you do not miss the next update, because this particular mystery is still actively unfolding, and the next major discovery could reshape the story all over again.